So this video is going to be about combustion reactions. So combustion reactions are a very important class of reactions. So whenever we burn something, we're doing combustion. And so combustion is one of the ways that we produce most of our energy, whether we're burning wood or coal or fossil fuels, which I guess coal is a fossil fuel. But anyway, let's look at combustion reactions. So generally, a combustion reaction is defined this way. Anytime you have some sort of stuff, an element or compound, so I'm just going to write stuff here, and you react that with oxygen. So oxygen gas in the air or another source. And what you produce, you're going to make some products. So I'll just abbreviate that prod. So you're going to make some products. And then the other thing that you're going to release always is heat. So these are characteristics then of combustion reactions. So what do you have to have? You have to have a reaction with oxygen and you have to produce heat. So those two pieces are essential. So now let's look at some typical combustion reactions. So we're going to look at combustion reactions of some organic molecules. Organic molecules are carbon-containing molecules. And in particular, we're going to look at carbon-containing molecules that contain carbon, hydrogen, and if they just contain carbon and hydrogen, we call them hydrocarbons. And so that term is in your book. Hydrogen and carbon makes a hydrocarbon. But we can also get the same result if we also have a molecule that just contains carbon, hydrogen, and oxygen. So if we have a molecule that just contains these three types of atoms, any numbers and any combinations, then when we react that with oxygen, O2 gas, and we burn this completely, so ideal conditions, everything works exactly like it should, then when we're done, we're going to make these two products always from this kind of combustion reaction. We'll make carbon dioxide, which will be produced in the gas phase, right? And water, which will also, because heat is produced, be produced in the gas phase. So we'll write H2O and then parentheses G next to us to remind us that this is a gas. So this material right here could be a solid, liquid, or a gas, and we react it according to this reaction. Alright, so let's look at a particular kind of CHO compound, in this case just a hydrocarbon, and this is the simplest one, CH4. So CH4 is methane, and that's the gas that makes up most of what natural gas is. So if we're burning natural gas, doing combustion, then that's going to react with O2 gas, and as we predict up here, we're going to make carbon dioxide and water. So CO2 gas plus water. Okay, so we've got a problem with this reaction in that it's not balanced. So I've got one carbon atom over here and one carbon atom over here, so that's okay, but I've got 4 hydrogens and only 2 hydrogens over here. So since my carbons are balanced, I'm going to follow that procedure that we start balancing the other atoms. And we're going to save oxygen for last because it's the simplest molecule, it's by itself, and I can just put a number here to balance things out. So over here, this methane molecule has 4 hydrogens. Over here, this H2O molecule just has 2 hydrogens. So I would like to have 4 hydrogens over here, so what can I do? I can put a 2 in the front right here. Maybe I'll switch colors on us. Yeah, so I can put a 2 in the front here. So I'm going to make that you can see that a bit better. There we go. So 2H2O. Alright, so now I've got 2 hydrogens. Now I need to balance out the oxygens. So over here on this side I have one oxygen molecule which has 2 oxygen atoms. So there are only 2 oxygen atoms over here. Whereas on this side I have one CO2 molecule which has 2 oxygen atoms. So there's 2 oxygens that I get from CO2. And then over here, water molecule. Each water molecule has 1 oxygen atom. But this coefficient is telling me that I have 2 of those water molecules. So I've got a total of 2 oxygen atoms, and 2 plus 2 is 4. So I've got 4 oxygen atoms on the product side of this reaction. So over here on the reactant side, I need to have that same number. So what can I do? I can put a 2 right here. Now this reaction is balanced. So I can't create or destroy atoms in a chemical reaction. I have to have the same mass before and after. It's the law of conservation of mass at play here. And so these coefficients will take care of that. So let's interpret what these symbols mean. Okay, so these symbols mean that I have one methane molecule. So let me draw a methane molecule. All right, so here's a carbon atom. Color that in. And then we've got 4 hydrogen atoms. So I'm going to select a different color up here, and we'll put those 4 hydrogen atoms on. So 1, 2, 3, 4. So each one of those white circles represents a hydrogen atom. So this is one methane molecule, carbon and 4 hydrogens, all bonded together. And then this is going to react then with 2 oxygen molecules. So that's what the 2 really means, is that we've got 2 of these O2 molecules. And I think I'm going to color them red. So oxygen is typically modeled as a red atom. So we've got 2 of these O2 molecules. So here's one O2 molecule, and here's another O2 molecule. So these 2 oxygen atoms that make up the O2 molecule, they're chemically bonded together, covalently bonded. All right, so that's what the 2 means, that we have to have one of these molecules and one of these molecules. Now what's going to happen? Well, somehow these bonds get broken, and we're going to rearrange things to give us the products. So the products, we're going to have, again, a carbon here. So there's our carbon atom. And that's now going to be bonded to these 2 oxygen atoms. So here's one oxygen atom over there, and another oxygen atom over here. So there's CO2. So we've made one CO2 molecule. How do I know it's 1? Because there's no coefficient up here, so I assume it's 1. And what's the other product going to be? Well, I'm going to have 2 of these H2O molecules. So there's an oxygen right there. We'll color that guy in on one water molecule, and here's an oxygen atom on another water molecule. So I'm going to color that guy in, and let's get some white oxygen atoms up here. So change my pen color, and so there's a white atom. Here's another white atom. So there's one water molecule that we've made, and here's another water molecule that we've made. So that's what this notation means. So we can think of this in terms of pictures in our head about what the molecules are doing. So this methane molecule is going to react with these 2 oxygen molecules, and somehow the bonds are going to break and they're going to rearrange. Some of the oxygens will stick here on the carbon. The other oxygens are going to stick to some of these hydrogens to make water molecules. Now there's another interpretation for all of this. So these coefficients can refer to the numbers of molecules, but equally well we could scale this whole thing up. So this is the minimum number of molecules that I have to do this reaction. But if I multiply this by 10 or 100 or a billion or whatever, it would still be balanced, right? As long as I have 10 billion of these and 20 billion of these, and I'd get 10 billion of these and 20 billion of these. So any number I could use. So why not multiply by Avogadro's number? In that case, these coefficients up here also mean that I've got 1 mole of methane molecules reacting with 2 moles. That looks like some sort of agent. Anyway, that's a mess up there. Sorry about that. Reacting with 2 moles of oxygen molecules to produce 1 mole. So that's what that coefficient means. 1 mole of carbon dioxide molecules and 2 moles of water molecules, H2O. There we go. I was trying to write a carbon again. So H2O. So that's what we get. So 2 interpretations. The actual numbers of molecules, or this can be, 1 dozen, 2 dozen, 1 dozen, 2 dozen, or 1 mole, 2 moles, 1 mole, 2 mole. So that's what these stoichiometric coefficients means. These are called stoichiometric coefficients, or just coefficients if you like.